It is my pleasure to give the session. My today's sessions will be the memory technologies for AI hardware, because now the present the technologies, if we see in the semiconductors, so the IoTs and the AI, the machine learning, the deep learning will play a very important role. So as we are moving into the latest technologies, so for that, so some of the glimpse about what are different memories technology will be used in the AI hardware. So let me put the glimpse. So the initial part about the memory, as we know about that, the memory is an integral component in all the computer system. So it starts from your smartphone and a packet what you are having the data centers and powering the world leading edge AI applications. As it continues in the now presently, so it may reach the complexity, and sometimes what will happen, it will create a demand for more memories from data center to endpoints. Because nowadays, if you see everywhere, if you talk about, it's nothing but a memory. So the memory will play a very important role. So now the data center to endpoints will create a reshaping the industry requirements and the traditional approaches to the memory architectures. So as we know that, so there are like as open AI, like nothing but your factory. And now, what about the amount of the computation the open AI will use in the largest training set will be increased at the rate of 10 times the per year under 2012. So every times, so the memory storage will be multiplied by 10 times. So once like company example illustrating, if I say, so we need the very huge amount of the memory is required in the open AI for the chat GPT normally. Then the most talk about, we can say, that large language model which is used. So now in the presently as we are using chat GPT 3 and 4, in the chat GPT 3, it's inbuilt which is using how many parameters are used in this, almost 170 billion parameters was used in the GPT 4. It's almost it's released. So even in VR also we are using 1.5 trillion parameters was used. But all these parameters when you use, whatever the information when you pass, everything was stored in the memory. So the feature very huge. So styrene, so like one more thing here. So very important thing. So within a short period of time, so one you can rely on that continuous evolution of memory technologies to produce this massive amount of data. What are the applications evolve? So here, when you say the AI application will evolve and it will become should be it is more complex. At the same time, it will be more advanced models will be there. At the same time, we need a larger amount of data set required. The massive data processing may require a lower latency and it requires a higher bandwidth memory. So has the higher bandwidth memory increases, it has increased the storage also. So how the AI will impact the memory system? So how the AI is impacted the present scenario. So if we talk about the looking back during 1990, 2000 was characterized by the centralized computing system that was revolved around the desktop and the workstations normally. So now in that desktop and workstation, we are doing the connectivity. So it's improved connectivity and the process improvements. The period from 2000 to 2010 that will be enabled here. Just we are shifting towards from the mobile computing, the smartphones and the cloud. The post 2010, so we might have seen connected the IoT devices and the sensors along with the shift towards for the fog computing and the edge computing. Later now presently we are moving into the processing of the data like effectively we are improving for, as I said, very important the latency. At the same time, we are going to improve the bandwidth and the energy use. So like this is what some groups here is showing, like how it is be processing the data which is closest to or near to the endpoints, which will improve the latency bandwidth. So now here you can see here this is nothing but your connected endpoints. Then when you are connecting the connected endpoint with the cloud, so there will be intermediate, you need a either it can be IoT gateways or the base stations, or it can be the computing, the cloud computing, or the edge computing. So now when you play this things, if you want to connect or if you want to compute, so you may require a huge memory. So the huge memory it may require in the sense of that everything semiconductors will play a very important role for the AI. So now for that, what are the memory requirements, especially for AI actually? So for that, what we need first of all, we need to know about what are the characteristics of AI workload. The characteristics of the AI workload will be the first one is like it's a data intensive operation. The second one will be it has high throughput, then it has lower latency. So when you talk about the data intensive operation, artificial intelligence system will move a very huge amount of data sets. So that such as you can take example the images, the videos, and the sensors data if you take. So those things and all will require more amount of data. So for that to handle those data volumes efficiently, so the data intensive operation will be play a very important role. The same time, when you are having moving a large amount of data quickly between the processor and the memory, because nowadays when you use the normal general computing machine, if you take the processor and the memory will speak. When it is speaking, when you are having a large amount of data, so we may need to speak very we need to talk I will quickly. So for that, we need at the same time we need to minimize the delay also in the task, such as training the deep learning models. So we need to train as much as so many models to get the high throughput. Next one, we go for the low latency. So here the low latency here in the sense like the AI memory is like it is very fast to access the data which is stored in a memory that will ensure it can able to access in a real time or the real time processing. Like example, if you take the autonomous vehicle and the IoT devices. So now when you are going for autonomous vehicle, let's say like our example, if you said the driverless car. So the driverless car will play a role with the memory will be, it's like already which is stored in that memory in the driverless car, like called as nothing but a short-term memory and the long-term memory. So in that long short-term memory, in the sense like how it has to take the decision in a very short in manner, so that will be stored over the based on that your vehicle will act. So the IoT devices also will be used in the autonomous way in the like normal of whichever presently we are using. Then we need to know about what are the challenges will be in AI memory design. So the challenge is very important. The one is nothing but the power consumption. The second one is nothing but the scalability. The third one is nothing but the bandwidth and the bottlenecks. So if we talk about the power consumption, the AI computation, especially when you're going for the training, and it may requires consume most of the energies. At the same time, the memory technologies will be optimized for the power usage to meet the sustainability and for the efficient goals. When you talk about scalability, how it can be scalable. So the memory systems need to be scaled with the increasing the complexity. At the same time, you need to increase the size of the AI model to maintain the performance. So one more important the challenge is the bandwidth in the bottleneck, because the normal the traditional memory architecture which are using for AI memory, it will struggle to provide the bandwidth required for the AI workloads, which leads to the performance constraints. What are the importance of optimizing memory hierarchy here? So the importance of the optimization memory will be, so the memory here hierarchy will be referred as like the layered structure for the storage solution. The layered structure in the sense starts from the cache memory, then the main memory, then will be the storage. So what are the optimization in the sense here? We can reduce the latency by storing the frequently accessing the data closer to the processor. The example, when you're having a processor, normally the processor will have the close to the memory starting with the cache memory. So when you want to access the data, so normally what will happen, the processor will send the instruction to the cache memory. So the cache memory already, which already fetched the data, will be in the cache memory. It will be very easy to access in the processor. That is what you can reduce the latency. So by storing frequently accessed data in the cache memory, it will be very simple to access. At the same time, we can balance the trade-off between the cost as well as the speed and the capacity across the different memory level. So it will ensure that the efficient data flow and the energy usage that will be addressed the unique demands in the artificial intelligence applications. Now, this is the one of the very important thing we need to know. What are the traditional memory technologies with the use in the AI, especially for the AI? As we have come across with the previous memories, if you take, that will be classified into two different classifiers. That is the random access memory and the read-only memory. When we are going for the read-only memory, only just it will be used for the data will be read from the memory. So when we talk about random access memory, the random access memory, nothing but we can able to read the data from the memory location, but as a meanwhile time, and write the data into the memory. So, but when you talk about RAM, so it has again classified into two different types. That is nothing but here SRAM and DRAM. Where the SRAM here we are using for the AI, that is the static random access memory, especially this will be used for the high-speed on-chip memory for the caches. Then we may use the DRAM also. This DRAM will be used for the high-capacity memory for to train the AI models and to for interfaces. So, such as what are the different DRAM, if you say, from the earlier generation or the old model, if you take the DDR2, DDR3. But now, with present, if you say the sense, we are using DDR4, DDR5, and LPDDR for the energy efficient artificial intelligence. But the LPDDR is nothing but the low power DDR. It is used for the mobile smartphones. Next, the one more memory will be the flash memory. So this flash memory also, which will be used, it's a persistent storage for the larger AI data sets. So now, first memory, as we discussed, we're talking about the SRAM. So as we know, the SRAM is nothing but static random access memory. So the static random access memory, what are the characteristics of SRAM in the sense here? It will be used for high-speed memory and it will be used directly on the chip. So very simple, will be close to the processor. Or example, if they say it's a cache memory, we can say. So extremely, it will give the low latency compared with the other types of memory because this SRAM will be very closer to the processor. So that is the reason we can reduce the time because we can keep on or off on we can access the data. So what are the applications in AI using the SRAMs? The example, as I said here, it will serve as a cache memory for frequently access the data, which will enable the processor to work efficiently without any delay. That will be caused by the fetching the data from slower memory layers. The second application, you can say, ideally for the tasks that requires the rapid data access, such as during the deep learning inference. Next, the memory is dynamic RAM. Here, the characteristic, the dynamic RAM, again, we can say the dynamic RAM, when it will be used in the sense, normally the dynamic RAM will have the capacitor. So the capacitor will store the charge. So the character of this dynamic random access memory will provide the higher capacity compared with the SRAM. But this will slow the speeds compared to SRAM. So SRAM will be higher speed compared to the DRAM normally because the dynamic RAM requires a periodic refreshing code of data, which is stored. Example, it is maybe around 10 every 10 microsecond or 10 nanosecond, we need to refresh the stored data, else which consumes the power normally. So the application when you talk, as we said in the A, that DRAM will be used, we are using DDR4 and DDR5. So now the standardized the dynamic RAM access memory generations will offer improvements in the bandwidth, especially including the bandwidth and the power efficiency. But the DDR5 is especially relevant for the high performance AI workloads, where the LPDDR, the low power DDR, will be used to optimize the energy efficiency. It may be suitable for the edge AI devices such as smartphones or the IoT system. There, we are using the low power DDRs. Again, when we talk about the DRAM, so it will be more essential to handle the huge amount of data set which involves the training and the inference process. So it may commonly used for the main memory in AI accelerators and the servers. So those places that DRAM will play a very important role. Next, the memory is nothing but the flash memory. So here, when we talk about the flash memory, it is a again non-volatile memory that will retain the data without the power. Generally, so this flash memory will slower than the DRAM and the SRAM, but it will offers the huge amount of storage capacity and the durability. The application, if I say the flash memory, it will act as a persistent storage for the huge data sets or the larger amount of data sets in AI, and it may use the pre-trained models. Some of the useful applications where the models should be stored and retrieved frequently. Example, the flash memories will be used in the autonomous vehicle or in the embedded AI system. What are the advanced memory situations? The advanced memory technologies at the same time again those are like the very basic memories you can say. The advanced memory which will be used for the AI in the semiconductor here, if I say, so one thing is high bandwidth memory, which will be shortly called as HBM. The second one is 3D NAND flash memory. The third one is phase change memory, we can call it as PCM. So when you talk about high bandwidth memory, that is called as HBM. So here, the high bandwidth memory, when you see here, the high bandwidth memory, it will be a type of the stacked DRAM. Normally, we can see in this picture over there, the package substrate, the interposer here. So like we are stacking the DRAM. So we can stack the DRAM designed to provide a very high data transfer rate. So it may integrate the multiple DRAM dies vertically. So it will be integrated to the silicon vias, that is a TSV. So what will be the data transfer in the HBM in the sense? It will be like up to 9.6 giga transfer per second. Example, or you can say 6.4 gigabits per second. That will be the transfer rate. So here you can say a 3D device which you are showing that will be resembles the small cube where the HBM will stacks the DRAM dies on top of each of the other to boost up the memory bandwidth in the system. Like if you want to increase the huge number, like we can keep on stacking the DRAM. So again, you can see here in this is our the package substrate. Then we are having the physical, like this will be your CPU or your GPU. This will be your logical die. Here, the HBM4. Here, normally HBM will have the version. This is the 4. The version is presently, which is there. Recent version is primarily it's designed to meet the demands of the generative AI and high performance computing. So it will requires the handling a huge amount of data set at the same time. It will perform the complex calculation very efficiently. So this HBM3, it has 12 layers normally. Like the data transfer speed is 24 gigabyte per second. So we can have this hardly going to be the client application. This HBM will be used in the client application such as like if you're using the graphics card there and all, which will be used. The higher bandwidth, the HBM will be support for the faster data rates. So like it will be making the capable of handling the significantly larger volumes of transfer per second. So if you want to transfer the data, like this is our GDD or 6 GDD or RAM, this is our processor. So if you want to communicate, say example from DDR to this one here, we are going to do this from processor to DRM. So when the DDR4 can deliver the speed, as I said, it's about 25.6 gigabytes per second per module actually. So we can say the HBM4 will offer bandwidth exceeding 1 terabit per stack actually. So here the GDDR6 is nothing but it's a graphics double data rate. So it is a sixth generation because the older generation than DDR4 and DDR5, this is the latest generation. So what is the advantage of this in the AI hardware industry? The first advantage is it's a data throughput is very high. So especially when you're going to handle the massive data flow will be required in the AI training and for the inference. The second advantage will be that design is very compact. So because if you are going to stacking the DRAM in the physical footprint compared to the traditional DRAM layouts. The third advantage will be when you are going to use HBM, it has the low power consumption because of the shorter data path and it has the efficient architecture result in the reduced energy. So it will be used critical for the energy efficient AI accelerators. So the application, when I say the SVM will be used, widely used in general purpose, that is GPUs and AI accelerators. The accelerators which is used for NVIDIA, that is A100 and the AMD Radeon Instinct. So those will support the data intensive tasks like deep learning training and high performance computing. There and the SVM4 was used. So this used now present also. Now, when we talk about the next, the trending technology is nothing but the 3D NAND flash. So when we talk about NAND flash, it is also a non-volatile memory where the memory cells will be stacked vertically in the multiple layers. So now to increase the storage capacitance. Now we can see here, this will be the only, it is a two dimensions and then when I'm doing multiplication here, they may get the 3D flash memory. That is nothing what here you can say. It is unlike your 2D NAND, the 3D NAND flash memory will offers the, the storage capacity and the reliability. So sometimes we may say this 3D NAND flash memory is a vertical NAND. The flash memory will market is driven by like smartphones and the solid state drives and all. This 3D flash memory only used. So here we can say this is our the layout structure of your 2D flash memory. So when you are comparing the comparison of 2D NAND on the 3D NAND, when you see here, you can say, so normally the electron storage in the 2D NAND will be a floating gate, but in the 3D NAND will be used the nitrate. That is the gallium nitrate will be used. So the current path when you talk about in 2D, it's like it's a bulk single crystal silicon, but in 3D, it's a thin polycrystalline structure. You can see in the structure here, we are having like it's a control gate. There is a floating gate over the drain to source. This is a single silicon channel over there. From this 2D to 3D when I go, so this will become as a control gate over there. This is nothing but our nitrate. That is what we said. The electron, the storage will be in the nitrate here. So this the channel will be your the polysilicon channel here, drain to source. You can the evolution how it has come from 2D to 4D, especially as I said 3D, even the 4D also is there from 2D. So it will go for the 3D NAND. The next feature will be the 4D NAND also. When you use this, what are the things we can able to know in the sense? The first thing is like what about the storage capacity of 3D NAND? The 3D NAND, the storage capacity will be when you are stacking vertically, it will increase the storage capacity as while reducing the footprint because we are doing in the stacking of vertical. The performance wise, if you say, so it allows for the shorter connection between the memory cells, so which may improve the performance also. At the same time, the power consumption. So the 3D NAND will cut down the power consumption on half compared to the earlier NAND chips. So cost, if I say the 3D NAND will lower the cost per byte compared to 2D NAND. But the design, the 3D will be difficult compared to the 2D NAND. But which has a planar structure, the 3D NAND will resemble the vertical skyscraper. When we talk about the layers wise, if I say the leading edge 3D NANDs, the fast parts can have 32 to 48 layers it will have. The interconnection when you're doing the 3D NAND has the tiny vertical channels will be connecting the layers. So what are the advantages for this in the AI hardware in the sense? First, the advantage will be when you're using the 3D NAND, it will be used for high density storage. That is the first thing. Second thing is it will be improved for the long life. Third one, we can say it will be a cost effective. So high density, I will say it will be very ideal for the storing the larger AI data sets models. Next, it will improve the longest life also because of vertical stacking. It will reduce the cell-to-cell interference and it will lead to better durability. It will be very cost-effective also for the scaling, enables for higher storage capacitance without a significant increase in the manufacturing cost. So the application, if I say where we are using, this will be used in the data centers normally and the edge devices for AI model storage and training and inference workloads. It may suitable for the cloud-based AI training pipelines also. It may require a more amount of storage capabilities. The next memory is nothing but the phase change memory. That will be called a PCM. Even this PCM also is one of the type of non-volatile memory. So that will use the phase changes in the material. So the phase changes in the typical, we can say, chalcogenide class. That will store the data. This material only will store the data. Here we can see here, this is the cross-section view of the phase change memory. This material can be toggled. Which material? The material which will be used here is nothing but chalcogenide cluster. So this material can be toggled between amorphous and crystalline. Where the amorphous means it is a high resistance, or the crystalline is nothing but a low resistance state. That will represent the binary. The amorphous will represent the high resistance is value logically 1, and the crystalline will be represent the lower resistance, the value 0. So it will have binary data. So now in this, we can say this is the contact. This will be our heater. So like these two are VIA and PCM array. So let me show with this. The PCM device is made up of the small amount of phase change material between the two electrodes. These are the two electrodes. Now the data will be stored by setting each cell. You have to set the first like a low resistance or the high resistance. So if it is a low resistance interference, the material will be crystalline, and the high resistance will be amorphous states. So if you want to change the state, then the heat source is used. So here, this is our heat source. Here, this heat source will be used over there to transform the material from the one source to the another source, either from the crystalline to the amorphous state or the amorphous state to the crystalline state. So that will be done with the help of the heat source, where the PCM will be made using the germanium antimony tellurium alloy. That is a material which is used for PCM memory, where this PCM will reads on the writes at the low voltage, which offers the service substantial advantages over the flash memory and the other embedded memory technologies. Now, when we talk about here, as I said, two electrodes will be there. This is the top electrode. This will be the bottom electrode. So, when I'm going the heater over there, it's a amorphous. The degrees is nothing but we're changing the. It is nothing but your higher resistance. As I said, amorphous will be used for the high resistance. That is what here we are saying. It's a high resistance. Then the heater will be low resistance. The 1 to 0, this is 0 to 1. So when you use this PCM memory, so the advantage of this will be here. The first one is something as we specified, it's a non-volatile memory. So it will retain the data even though if there is no power. So it will be energy efficient. So it will be there for up to how much year in the sense we can say like for around 10 years at the room temperature. So it will reach or write the data in a very high speed, the PCM. Normally, it is very faster than the NAND flash memory, but it enables the real-time AI interface. Then it will change the individual bits without erasing an entire block of cells. That is one of the very important characteristics of the PCM. So to change individual bits without erasing an entire block of the cells over there. But when you talk about NAND flash or then in the memory, sometimes we may need to erase the entire block cells. The endurance cells here, it will be more durable than the NAND memory, particularly under the high write cycles. So here, this memory where it will be used. So particularly it will be used in the AI inference system where frequently where you are going to use for the read operations in the domain. Example, if I say the emergency use cases in neuromorphic computing. So to mimic brain like architectures for advanced VA systems. So there, this PC memory will be used, especially for high performance computing, and where the embedded system, which will be used like for industrial or the medical devices, then we may use for the solid state drive. Then in memory computing, the sense normally you will have memory and processor separate will be there. So that is what the general processor will communicate. But when you talk about an AI, like hardware, if I say here, it is nothing but in-memory computing. The memory will be along with the processor. So that will be communicated. Example in the sense that in-memory computing will be used in the machine learning application. So because when you compute in-memory computing, the data access will be very fast. So next, what are the emerging memory technologies are there here? There are again, if we talk about, there are various emerging memory technologies are available. There are resistive RAM, magnetic RAM, and the ferroelectric RAM. So these all are will come under the which one we can call as the classification under the DRAM only. So the resistive RAM, so again shortly called as RERAM. So it is a non-volatile memory technology that will stores the data by changing the resistance of the solid dielectric material. The second one is nothing but magnetic RAM. So even this also is a non-volatile memory that will store the data which using the magnetic domains, not the electric domain. So it's made up of an array of magnetic tunnel junctions that are connected by the bit lines and the word lines to form the circuit. Next one is ferroelectric RAM. So even this also is a non-volatile memory that we stores the data when the power is interrupted. So it is like similar to the DRAM construction, but it uses the ferroelectric layer instead of dielectric layer. The first, let us see about the resistive RAM. Here, there is a type of non-volatile memory that will store the data by changing the resistance of the material. So normally, it uses the conductive filament or the ion migration that will be switched between the high resistance value to the lower resistance value or logical 0 to logical 1 state. So when you talk about here as a resistor RAM, here you can say this is a voltage, this is a top electrode, this is a bottom electrode, here metal oxide. This is our 3D view structure. This is a conducting filament, the metal oxide, top electrode and bottom electrode. As we said here, it uses the conductive filament or the ion migration that will be switched between the logical 0 state or the logical 1 state. So here you can see here, we can have the resistor RAM as a high resistive state. So like how can say it's high resistive state? The logical low will be referred as 0. When a voltage is applied across the resistor RAM to switch at the states from the high resistive state to the lower resistive state. That is HRS nothing but high resistive state. The LRS is nothing but low resistive state. Where HRS is nothing but again I can say value will be 0, then it will be 0. Where the BE is nothing but the bottom electrode, where T is nothing but the top electrode. So now we can see here, this is nothing but with the chart like how it's moving over there. This is the transition we are getting, like a high resistance state from 0 to 1. So logic. Since the filament is a detached state during the high resistance HRS state, that is a high resistance state, there will be no proper path from the current to flow over there. This is what here we can see, like there's a gap increases. So here, this will be nothing but your CF is nothing but where we are showing the conduction filament actually. The CF size will be increases. See that conduction filament size will be increases in the sense there will be a flow of current in there. What is the advantage of a hardware? So when you're using this resistive RAM, there will be the advantage will be like the efficiency, energy efficiency. It will consume the less power compared to the traditional memory technologies. It may use it for ideally for the power constrained environments. So it is a non-volatile memory. It will retain the data without the quantum power supply, and it may suitable for the low power AI devices. Then the speed performance is very high speed. So uh, comparatively with the NAND flash memory, this will be very faster at the same time comparable to DRAM for the certain applications. So when you talk about this resistive RAM here, when you talk about the energy, when you talk about the energy, it may retain the data without the power, and it is like 5 times of lower the energy than the E-flash memory, then 20 times of the lower the energy than the NAND flash memory, 30 times lower the energy than SPA flash, 40 times lower than the energy in the Bluetooth low energy. About the energy on the top. When you talk about performance, like 100 times lower read latency, 1,000 times of the faster writes, then no errors is required, then 10 years the retention of the data at 85 degrees centigrade, then endurance will be 1,000 times, then the temperature of the data will be still like 40, minus 40 degrees centigrade to typically 125 degree centigrade. About the density, when you talk resistive memory, like it has the twice the denser than 3D NAND memory. Then it is a stackable also. Then 3D cross point array also. So the capacity will be from megabyte, gigabyte to the terabyte. It will be very scalable. So below 10 nanometer also we can do. The density can go. Again, this will be used in the applications like AI at the edge computing. The resistive RAM will be widely used in the edge AI applications, such as the smart sensors are used resistive RAM on the IoT devices also, and mobile AI platforms where the low power and the quick access to memory are the critical part. Next, the application will be neuromorphic computing. So, neuromorphic computing is nothing but to mimic the brain neural architecture for the advanced AI hardware. So, it will be used in the various systems. It will be used including the power management IC, then MCU and microcontroller and the AGI and many others applications will be used. Next memory is magnetic random access memory. Now, the MRAM will be uses the magnetic states to store the data, not the electric states here. So it will be rely on the magnetic tunnel junction to read the data and the write the data. So that will combine the benefits of the speed and the durability. So even this also is a non-volatile memory. So it will be uses the electron spin. That is what you can call the picture spintronics. So it uses the electron spin to store the information. And MRAM device is a spintronic device now. It's a spintronics device, one of the latest technology actually. So now here you can see it will be a control. So the magnetic material which has the piezoelectric material will be there. So here this will be the control voltage over there. So it will be on this in between. So we can show here in this picture how this magnetic memory. So here this is what the basic cell of a spin transfer torque MRAM we can see. So like in between you can see in this is what the pixel layer, the free layer, and this is the array layer. Here this is what we can say the current flow will be in this way. That is the spin products. So this MTJ, that is nothing but magnetic tunnel junction. That is MTJ. The magnetic tunnel junction, that is I think the MTJ, they consist of two ferromagnetic electric layers and one tunnel barrier layer. So here the one layer has a fixed magnetic direction. And the another layer will change the direction based on by the external field or the spin transfer path. So at this time, if it is a high resistance, then we can say it will be in the logical one state. When it will be in the logical one state, if the two ferromagnetic layers are different direction, then it will be in the logical one state. If the two layers are the same direction, then it will be in the logical zero state, or we can say it is the lower resistance. Where this M RAM will change the three layers magnetic direction via the spin polarized current that will enhance the scalability and the immunity from the schematic field. So like the read operation. So how the read operation will be performed here in the sense, the read operation will be begins when the word line, because here we are having the BL is nothing but a bit line, where the WL is nothing but a word line. The word line is nothing but your gate terminal. Now here, when you are reading the operation, that's the read operation begins when the word line is selected, that is WL, and the voltage is applied between the bit line, that is a BL, and the SL, that is nothing but your source line. When I'm applying the voltage between the BL and the SL, then the word line will be selected. Then the current will be passed through the MTJ, that is nothing MTJ, or it will not be depending on the state of the MTJ, which can be sensed or it can be measured. So similarly for writing operation, the writing operation will be begin when the WL is selected and the positive voltage difference will be established between the SL and the BL. For writing a logical 0 or a negative voltage difference is established to write the value logic 1. So here the current amplitude will be required to successful write in the related material of the tunnel barrier layer, the writing the pulse duration. What will be the advantage of this memory? So here it is a first advantage which is non-volatility. So it will maintain the data even when the system is power off. Second, it's the speed because it offers the ultimate speed comparatively with the SRAM, but with the low power consumption. About the durability, which you say the resistance to bear out from frequent write operation make it highly reliable. When we talk about application, it's a AI accelerator. It enhances the efficiency of the custom AI chip by reducing the latency, and it will provide the quick memory access. At the same time, the embedded system also that is used in the autonomous vehicle, then industrial AI devices, the robotics, where the robust memory is needed. Next memory is nothing but ferroelectric memory, that is FRAM, where the FRAM also is a non-volatile memory that uses the ferroelectric layer to store the charges. This is nothing but a ferroelectric charge. So it will provide the combination of speed, durability, and energy efficiency, where this FRAM will be used in portable medical devices and the automotive systems. So here we are having a row line that is nothing but a word line and a row line. So simple, we can say RL and BL will be here, the word line and the bit line normally. So now, advantage of this AI hardware will be, first advantage is the lower power consumption. It may requires less energy to make diaphragm ideal for the battery powered devices, especially for the battery powered devices and all. This type of memory will be used. It has high endurance. It will endure a high number of read and write cycles without any degradation. So fast access span. So it can operate at very speed close to the SRAM by enabling the real-time processing in AI applications. It will be used in the IoT devices, like it will be used in the sensors and the wearable devices to process the AI algorithm efficiently. Then also it may be used for the AI hardware for the edge computing devices. It is suitable for the compact and the low power AI system, especially in the healthcare and the smart home devices. These are some common memory systems for AI applications, as we said here. Example, on-chip memory. Then you're having HBM, as I said here. Then GDDR, the Microsoft Brainwave, the Graph4 IPO. I said these two are something but your highest bandwidth and the power efficiency. Then very high bandwidth and the density will be like AMD, Radeon, RS, of physics, and NVIDIA Tesla V100. This will be used. Next, there will be some good trade-off between the bandwidth and power efficiency, cost and reliability between these two. applications like NVIDIA GeForce RTX 2080 Ti and AMD running that. So these are some multiple options will be suited for the different needs actually. So now we may ask the question, why these technologies will be matter for the AI hardware? Because when you are merging the memory technologies addressed by the key challenges, so nowadays will be faced by the AI hardware, which may include the power efficiency and non-volatility, speed and scalability. Because when you are reducing the energy footprint of the AI devices, particularly in edge devices and the mobile environment. Next, it may ensure the data persistent and will be reliable during the power interruptions. It may support the growing demands of a workload with a fast and scalable memory solutions. So sometimes the industry trends and the application here. Like based on this, what are the trends in memory technology for AI hardware here? So the AI specific memory customization will be the modern AI workloads will be highly diverse. At the same time, it may require a tailored memory solutions for the efficiency. The example you can say which includes the optimized DRAM configurations for the deep learning and the custom memory entirely for AI accelerators. Those customizations will be which will enhance the bandwidth of the memory, then it will reduce the latency and will minimize the energy consumption for some AI specific tasks. So here the quantum memory for the next generation AI actually, because the quantum memory will store the quantum information, that is qubits normally used to call, and it will be crucial for enabling the quantum computing advancements. In AI applications, normally the quantum memory will promises the unprecedented data processing will be capabilities for which solve the complex problems at the scale. Thoroughly some in the early stages and all, it will be poisoned to revolutionize areas like optimization, machine learning, and the cryptography. What are the applications here? The application, as I said earlier, that is will be used NVIDIA GPU with HBM, the second edition of AI training. Then they are using the Google TPU memory integration, that is a Google Tensor Processing Units, which will be especially specialized for AI chips designed for the machine learning workloads. So this Google's TPU units will be integration of memory with the computation unit will be reduce the latency and it will boost the performance of the task like natural language processing and the image recognition actually. Where MRAM in edge devices very importantly, that is as I discussed, the magnetic RAM will increasingly will adopt in edge devices where the power efficiency and reliability are critical. But the applications, say example, when you say IoT devices, the wearable devices, autonomous systems that may provide the fast and reliable memory for the real-time AI interface. Now, some of the AI-powered wearables. What are the AI-powered wearables? Nowadays, so many wearable in the health sector has come. And then one of the things, Aura Ring. So this Aura Ring will be used to track various health metrics, which includes the human being, the sleep quality, the heart rate, the body temperature, and the activity levels using the advanced sensors. So this Aura Ring will be used by AI to analyze the data such as the heart rate, the variability, to analyze the body temperature and the data movement also, which will provide the personalized insight and recommendation. Once in this feature, it will be ability to calculate the cardiovascular age also and the cardio capacity also. It will offer the users of glimpse into their long-term heart health it will give. So this rings AI algorithms analyze plethysmography, we can call it PPG, so as ECG signal we said. So here it will be analyzed with PPG signal to estimate the arterial stiffness and the pulse rate velocity. The second wearable device, Whoop, with also a AI-powered wearable device that will be focuses for optimizing the athletic performance and the recovery. So it will be continuously monitors the heart rate, the sleep, and activity level, especially for the athletics for them. It will provide the users with a comprehensive understanding of their body needs, what is and all is required. The next variable is something but Fitbit. Even this Fitbit is a versatile smartwatch. It's a smartwatch actually that combines the advanced health tracking with AI-powered insight that will monitors the wide range of health parameters again, which will increase the heart rate, the sleeping stress level, and the skin temperature. So one of the key feature of a Fitbit is the stress management capability. So actually, this watch will use the electrodermal activity sensor. It will should detect our human being will the stress level it will detect and will offer the guide breathing exercise to help the user manage to reduce the stress effectively. So what will be the future now actually? The first one thing is we can say like the bridging the memory compute gap in a system. The memory compute the gap will refers to some disparity in between the speed of the data processing unit and the memory ability to supply the data at the equivalent rate. This is the one of the very important change, the bridging the memory and compute gap in AI system. This gap will cause the bottleneck in AI system, where especially some tasks may require larger data sets and high-speed computation. One of the example, if you want to say this one is nothing but bottleneck in the sense your GPT. Also, we can say or autonomous vehicles. There also we can say. Next to the solution for this, what we can do, one is nothing but in-memory computing, because one of the very good solution is the in-memory computing. If perform the computation will be directly in memory to reduce your data transfer delay. Next is near memory processing. So that also will be placing the processor very closer to the memory to reduce the latency. Next one is high bandwidth memory. So here, if you are using the high bandwidth memory, so there is a possibility of to increase the data through bit to bridge the gap. The second feature will be the role of non-volatile memory in the edge AI. It will be more critical for edge AI devices, which will be operate in a resource-constrained environment like IoT sensors or the autonomous drones. Why it matters for edge AI? So there are some parameters will be there for edge AI. There are like energy efficiency, compact design, and the real-time process. So energy efficiency will be due to the non-volatile memory, which may consumes less power, and it will be extending the your battery device life also. Then design will be very compact that will enable the smaller and more efficient edge devices. Next, it will be fast access speed that will be essential for AI interferent task at the edge. Next one is the green computing. The future is like energy efficient memory technologies. The green computing will be a reference here to like the sustainable for the practices and the energy efficient technologies in computing the systems. What the memories role over there actually. The memory role will be like the advanced memory technologies like the low power DDR and the high bandwidth memory will reduce the energy consumption for the operation. Then the innovations will be like near zero standby power in magnetic RAM and the resistor RAM will contribute the lower energy footprints. That will be very crucial for larger scale AI deployment in the data centers where the memory contributes significantly to the power consumption. Next here, one of materials using flexible silicon everywhere we are using. One more thing, the new materials like the gallium nitride and the advanced the fabrication techniques like three-dimensional chips will hold the opportunities will to provide the smaller, the faster, and the more efficient solution to the IoT devices. So with this, so we can make it like the memory technology stuff will be more critical for the AI hardware enhancement, and it will be emerging innovations. So it will address the power, then it will address the bandwidth, and it will address the latency challenges. This is all about what are the memory challenges the memory will be in the AI hardware. This is all about the today's presentation. But one more thing here in this, as I said, the memories in the autonomous vehicle will be used short-term memory, long-term memory, like which will use the taking the auto route. Everything will be used as a short, like frequently it's going to the route. It will be take as a long-term memory which will be stored. But meanwhile, like 1 or 2 days, the shortest memory and all which will be used. Even the autonomous vehicle will be both the long-term memory as well as the short-term memory. Also, it will be used because especially autonomous vehicles and all, if you say the memory will play a very important role because everything, all the routes as will be deployed in the memories, everything. Based on that, only it will run. Even not only that, so even other devices which you said here, like the IoT sensors, the memory also will play a very important role, as well as the wearables also will play a very important. Everywhere when you talk about the main important thing, memory only, memory. Even when you talk about now present the cloud storage, what you're talking, even there also, or what you are telling about chat GPT, even there also, memory only will play a very important role. As now present, the GPT-5 may was to come actually under the research actually it's not yet released. The GPT, chat GPT-5 actually it has uh, the parameters, if you say compared to GPT-4, will be like double or triple actually the parameter, which will be more effective. Yes, thank you. Is there any other queries?
Good afternoon, sir.
Yes, madam. Good afternoon, madam. Yes,
Is it
madam. Yeah.
audible, sir?
Yes, madam. Audible, madam. Yeah. Yes, madam.
Sir, it was a very nice session, sir. Actually, AI in a hardware, it's a very new topic. And you have
Thank you,
covered
madam.
all the topics with respect to industrial perspective, the application perspective. Sir, one small this inquiry,
Yes.
because you have highlighted more about the advantages of this topic. Any
Yes.
limitations are there, sir?
Yes, madam. So actually, the limitation, if we talk like, so the advantages, so like whatever the advantages we said, so in that, sometimes what will happen when you're using the technology or the scaling or the power, even that will be limitation for them actually. We cannot say particularly what will be the limitation actually. So even I'm not gone through that much actually.
Okay, sir. It was a very nice session, sir. Thank you, sir.
Yes, madam. Yeah, thank you, madam. So I request all the participants to enable the camera for to capture the snaps. I request all the participants to turn on your camera to just to yeah. Thank you. Thank you for everyone. Thank you for all the participants to participate in the FDP. So we join the tomorrow's session.
Thank you, sir.
Sir, any doubts from participant side? Feedback link has been posted in chat box. You can utilize that. Thank you so much, sir, for your wonderful session, sir. It was very great session.
Thank you, madam.
Shall we wind up the class, sir?
Yeah, yes, madam. Yeah.
Okay, thank you
Just
all.
you can, yeah, just you can post this link in the group, madam. Feedback
Okay,
link.
sir. Okay, sir.
Yes, madam.
So thank you so much, sir.
Yeah, thank you, madam.